Uh, Thank you, Dr. Shasuta, for again welcoming me. And thank you, participants. I think a good number of participants has already joined. So let me share my screen. Okay, is it visible?
Yes, yes.
Okay. Okay, so today we are going to discuss about the mainly the fundamentals and the foundation of the deep learning and how the deep learning is predominantly applied in the healthcare data analytics. So that's what the things we are going to discuss today. So to begin with this deep learning healthcare data analyst using deep learning, I am quite interested to first of all convey the concepts of the deep learning in a detail, and then after I will try to cover a few of the applications of deep learning in healthcare. So that will be my flow of the session. So I welcome everybody again for this on the healthcare data analytics. So like deep learning is nowadays very popular, especially when the data, the underlying data is the image, and it is not only applicable to the images. It is applied on the different types of data as well. However, most of the application which you can find on the deep learning is where the underlying data is image, where suppose you are trying to uh, identify whether the your eyes are diabetic or not. So in that context, the recently the AI, the Google has a breakthrough in the AI where they apply this deep learning approach on the retina images to identify whether the eyes are normal or the having the diabetic eyes. So, but before we jump into this core concept of deep learning, we need to understand that from where this deep learning has originated. And for that, we need to trace back early in the decades of the 1950s, initially where there was a buzz around the artificial intelligence. Uh, if you can remember, in the days of the 1940s and the 50s, just after the World War II, the mathematics was the main subject or at the time where most of the ideas and concepts are delivered or formulated in the terms of the mathematics. And at that time, there was a buzz that whatever the things that we are doing manually, if the same thing can be done by the machine, then it will be helpful for the human being to alleviate some of the tasks which are not the our core expertise. Suppose if I want to give an example, the high-end example, I wanted to have a self-driving car. So in that case, the driving the car is not my core expertise, and I neither wanted to be expert in the driving the car. As a professional researcher, let us say we are interested to do the research, and therefore we need to read the several research articles, and we need to perform the experiments. So we are interested to do their task rather than driving a particular car. And for this kind of task, if we alleviate the workload to the machine, that it will drive the car and we will simply sit in the car and do our work. So as an example, suppose I am traveling from Greater Noida to Delhi. So it's around 50 to 60 kilometers of the road, and it nearly takes 1.5 hours. And if it is a busy schedule like traffic, then nearly 2 hours it might take. So if I assume that in a month of 30 days, if I travel only 25 days, excluding the holidays, then nearly I spend 50 hours one way by simply driving the car in the traffic. And that valuable times can be devoted to the research or some another fruitful activities if there is a something available like a self-driving car. So that was the fundamental thought process at the time of these 1950s. However, the example was quite a simplified at the time that they wanted to automate and they wanted to have something which like a game. It can be a chess or it can be AlphaGo, where we always required at least two players to play a chess. So suppose if there is a vacation and I'm getting bored at the home and I wanted to play chess, but there is nobody around me. And so what I can do? I cannot play chess because I'm the only player available. I need some partners. And if at that time I have somebody else like a machine which can play chess with me, then I can spend a time over there. But in order to make the machine to play chess, we need to inbuild some intelligence, and that's not easy considering the complexity of the game chess. So in the 1950s, the concepts of the artificial intelligence has been derived, and it was up to the 1980s that people were talking about the artificial intelligence, and then it started the coming the machine learning, the concepts where the the idea was to shift from the complete intelligence to first of all train the machine on some known data sets with some known outcome, and then after let the machine to predict something. So that was the concept of the machine learning, and the popular example which is nowadays quite saturated is that spam filtering. In each and every mailboxes we used to have that particular box, that is a spam box, where we used to find the emails which are not relevant at all to us. So why we are having that spam box nowadays, which is quite accurate, except the few cases, because on daily basis the spam filter model is being updated. So today, let's say the Google is having this spam box, and let us assume that roughly that they are delivering 1 billion emails across the world. So those all emails are acting as a training data for them. So in each and every day, the model, the spam filtering is being updated. It is trying to learn the new things which it to understand which email is legitimate and which email is spam. So that was the machine learning. So the thing is that there are different aspects of the machine learning, like a supervised learning, unsupervised learning, and then uh, reinforcement learning, but that not come under the machine learning aspect. So in the supervised, like this spam box filtering, first of all, the emails with the actual outcome, like whether this it's a spam email, this one is a legitimate, this one is a spam, this one is a spam. So first of all, the model will be trained, and then after the unknown data will be given. Unknown data means in this case the email will be provided to this model to predict whether it's a spam or legitimate. And based on the prediction, we ultimately try to identify or evaluate the model's accuracy, that how far it goes to correctly identify the outcome. And then after this machine learning in the recent decade, like from the 2010 onwards, we started hearing about the deep learning. So now there is a transition shift, and the core reason behind this transition shift, because in the machine learning we need two different things. One is a training data set, and another thing is that the feature. So we have only the training data sets, and if we don't know about the features, then also we cannot train the model properly. So this feature identification and the feature extraction is a very cumbersome process, and it requires a domain expertise. So suppose I wanted to design a prediction model on the training data set of heart disease. So unless I am having some sorts of understanding of the heart disease domain, I am unable to identify the features that help us to whether the person is having a disease or not. And that is not helpful as a researcher of the computer science, because today I am having a heart disease data set. Let us say I've spent 1 month of the time, and then after I have obtained the some expertise. But The next day we have the another type of the data set and we don't have any domain knowledge. So computer scientists, it is not our task to go to the different domain and get the expertise. Our task is to apply the intelligence. And therefore this feature extraction process, we need to eliminate at some up to some extent, and we just wanted to provide the training data. The machine itself has to identify the features, extract the features, learn based on the features, and go for the prediction. And there what becomes as a deep learning, where the feature extraction process is minimized, or we can say completely eliminated, which it can be done automatically machine. And that's why it's a breakthrough process, and we are predominantly applying the deep learning concepts. So if I wanted to just give the brief idea about these applications of the deep learning, then broadly, there are the three areas where the deep learning is currently being applied. So one is the computer vision, another is for the speech and audio, that means the signal. The first one, the computer vision, so the images are there, in the three channels, mostly red, green, and blue. The second one is the speech data, that is a signal form. And the third one is the textual data, where we can say the natural language processing. So as I told you that mostly the deep learning is applied on the images, but it is not restricted to that domain. It is applied to the textual data as well as the signal data also. So under this computer vision, we can have this deep learning for the image classification. So suppose we have taken a picture uh, just uh, just before this standing before the Taj Mahal, and I wanted to annotate that which object belongs to which category. Suppose it's a Taj Mahal, these are the person, these are the trees. So that's what we can say the image, sorry, the object detection. And the image classification is that I give we have predefined classes of the animals, and I wanted to identify that this particular image is belongs to the which particular category of the animal. So that's what we can have the image classification. And for the speech and audio recognition, we have the language translation and the voice recognition. And for this natural language processing, we have the recommendation engine and the analysis. So one example in each category, let me code over here. The voice recognition system. Uh, you will definitely relate this because we have nowadays several applications where from the voice command, it automatically understands that what we are supposed to ask the machine. So we have the Alexa. So suppose you say if you have a system at your home and you say switch on the lights, then what we are doing, we are ultimately speaking something. So the command is based on the voice. And the thing is that first of all, the machine has to understand that what words has been spoken, and then after it has to identify what is the actual command. So this voice recognition and understanding is the another area where the deep learning is applied. And I have some bank application like the Kotak Mahindra in my phone. So if I say what is the balance of my account, then it immediately shows me the balance. But if somebody else apart from me tries to say the same thing on my phone, okay, like say okay Google, because the Google and Kotak Mahindra has collaborated in that particular application. So I first of all need to say okay Google, what is the balance in my Kotak account? So it immediately shows me the balance. But the same thing if my wife speaks, then it doesn't open the balance. So that is a voice recognition. This voice is the legitimate and this voice is not legitimate. So that's what we can say in the speech and audio. And in natural language processing is also the same. Right, the deep learning is applied for either the summarization process or to know whether the particular product is good or not. So oral sentiment analysis. In fact, if I just want to give you the idea how complex the problem is, so I was sitting one day and trying to search for a Xiaomi phone, like Mi phone on the Flipkart, and I have seen several comments, maybe nearly 50,000 comments for a particular product of the Mi phone. And I was wondering that if I wanted to summarize the overall sentiment of these 50,000 comments, like this product is good or not, then what I should do, because I cannot go each and every comment, read them and comprehend that overall uh, view of this particular comment is positive, this one is neutral, and this one is negative. So that is just about the one product with 50,000 comments. But if I have this some popular cell phones like the iPhone, maybe you will find several comments. So it's quite difficult to first of all gather the data, and all of them are the first of all unstructured data. So you need to transform them into either semi-structure or the structure form, and then you need to build a model which process in a natural language fashion and get the overall opinion of the particular comment. Now, once you have the overall opinion of the particular comment, you need to go to the another comment, and each comment will have some opinion, either positive, negative, or neutral. And then after you have to fuse all the data to identify this particular Me phone is popular or it's a positive feedback from the overall mass, or it's having a negative feedback. So that's what the complexity of the idea and where we have to apply the deep learning. Now, that was the applications. But if you finally see that the problem formulation perspective of the deep learning, either we are doing some sorts of detection, we go for the prediction, or we go for the generation. Either you are doing any one of these three things when you apply the deep learning. So let me go back to the previous slide. So when it's a detection, so you can see that in the computer vision, we're trying to find the object detection. So when there's a car object, so we put a bounding box over there. This is a car, this is a person, this is a tree. So either you are going to detection, or you can also go for the prediction. That is what the second part. So in the second part, you are predicting that this particular image is an animal, or this particular image is a bird, or this particular image is belongs to some university or the building. So either you can predict that also, or sometimes you also require the generation. So the generation I will explain bit in bit detail then later after in the subsequent slides. So let me go and briefly explain you about the detection, and we quickly go over to the subsequent slides. So the text and the speech detection, like as a voice recognition, this is a legitimate person or not. When we have the voice-based command system, or we wanted to, let us say, the human behavior detection, whether that's the abnormal crowding, or there are some congestion in the groups, or the groups of the fleeing people. So this kind of human behavior analysis is helpful, in particular in these democratic countries like India, where protest is quite normal. But sometimes these protesting people go violent, and you need to constantly monitor the behavior of the protesting people. So if you have the human detection system there, then you can say, okay, there is some crowd in this particular area, let us say the Ramlila Maidan in Delhi, and they currently the behavior of this crowd is normal, they are not like very angry. But sometimes you may have the detection like the crowd is becoming abnormal, they are angry, most of the people, based on the face recognition. So that kind of analysis can also be done. And you can also have this fraud detection. So that's part of the security, cyber security part, but that can also be done when you apply this deep learning on the suitably formulated the problem. The another area where this like a prediction is sometimes like recommendation prediction, that what you are supposed to buy based on your habits and based on your likings and disliking. So there is the area where the deep learning can be applied. The individual behavior. The previously was this the crowd behavior. So individual behavior is also very essential because nowadays we have this suicidal rate is very high, particularly among the youngsters. They are very emotional, and sometimes they appear for they embrace this failure, then they unable to digest the failure, and they do commit something which is not expected from them. So you can also predict the individual behavior based on the facial recognition. So suppose I wanted to have a look on my employees in an IT industry. So it's quite common. We have the cameras in the building, and they have the cubicle arrangement, and people are sitting over there and doing their work. Cameras are constantly monitoring the surroundings, including the employees, and it constantly monitors their feelings or their behavior. So whether they are very feeling anxious, they are tired, or they are upset, they are happy. So in each and every moment, they try to identify the behavior, and on the cards of the time, on the due cards of the time, they try to predict whether this person is quite upset with something or he's not feeling good from the morning. Based on that, the company may take the precautionary measures to assist the employee. So that can also be the one of the ways you can go for the prediction. And the third one is the generation. So this is quite interesting nowadays because of the popularity of the social media websites. What we are used to have is that everybody is crazy and needs an attention nowadays. So what they do usually, they put some pictures when they visit Singapore, Dubai, like the Burj Khalifa, and they put it on the Facebook or Instagram so that several people will give the feedback. They will like the image, and they will put some comments. Okay, so you have been to Dubai or Singapore, and that's nothing but some sorts of appreciation, and it's some sort in some way it satisfy your ego that I'm being noticed by the uh, people. And but there is a limitation that you can go to Dubai once in a year, but what you will do rest of the time. So the people are nowadays have developed several different type of web applications which help you to look something differently. So the one of the examples see on that the visual art on the top side, where the style transfer has been used for the generation of the another image. So we are generating a data. So the two different images, like the one like original image, the another which you can download from the Google as per your choice, and you will fuse those two images to generate something new, the third image. And this concept is now a bit older, so you won't relate it much. But initially, when the fusion of the image has been introduced, the people were very excited. Oh, so awesome image has been uploaded. So they have received several likes on that. So that's what the people are doing. Similar to this visual art, we have this music also, where two different genre of the music can be fused to generate some another music. And similar to like this text summarization, where we generate out of the whole bunch of the text. So that's also we are applying the deep learning. Uh, so I just got a brief example to relate this text summarization. So suppose we are nowadays very busy, and that's why we unable to get proper time to read the newspaper. Uh, but I'm very much interested to know the current affairs. So in that context, what can be done to assist those people who are very busy? So every morning, previously, like a few years back, we have the physical newspaper. Nowadays, also we have physical newspapers, but we have this Google News and several other online news articles also available. So what if I design a crawler which in each morning at 6 a.m. starts crawling the popular websites and the news article, and in just 1 and 2 hours it tries to summarize the news so that which I can play at 8 a.m. during my cup of tea, that it will speaks that this is what the summary of this news. Suppose the people are protesting at the Delhi, so they say there is some sorts of negotiations are going between the center and the farmers, and it is expectedly to have this breakthrough in the near future. The UK's have developed some new variant of the coronavirus. So people are very, the flights are getting cancelled. So all those news which can be summarized in a 15 minutes. So what we are doing over here, that from the existing material, we are trying to generate something new, which is a summary. And now we go to the different aspects of the deep learning, and as well as the real application where the complexity is quite huge and the risk is also quite huge. So I have put intentionally this slide over here because this is a very positive news in terms of this computer vision. So the applications of AI in airline industry, though it is not related to this healthcare, but you can see the power of the deep learning. So usually we need the pilots uh, to conduct this landing and the takeoff. Once the plane is took off and it goes to the air, then after we can change the mode to the autopilot mode. However, the landing as well as the takeoff are the two very crucial things where we are still not relying on the mode and we require the pilots over there. So what they have experimented, that can we conduct this automatic landing without the need of the human, like in the case of the pilot. And for that, there is a technical universities of this Brunswick. They have successfully implemented a system which has automatically landed a real plane on the runway without any problem. So what the on the left hand side you can see the image that this AI pilot, artificial intelligence pilot, sees the runway and the lands automatically so that it can perfectly align the plane towards the runway, and then after it lands successfully. So this slide has been put to so that it is possible, if you properly in the model, then it is possible to do this kind of complex task also. Now let's come back to these applications of the DL in healthcare. So automatic injury diagnosis. Uh, so suppose there is some sorts of minor injury which cannot be easily visible by the human eye or with the doctors. And what can be done in that case is like this. In this case, in this particular slide, it is quite easily visible that there is some sort of injury. But there are cases where it becomes for the even experts to clearly identify the place of the damage. So there are advances in the deep learning where the images are given to the model to identify the cracks and the problem. So you can see that on the left hand side, uh, the image is given to the deep learning model to do binary classification. The one class is that the healthy leg, the another class is the broken leg. So the machine has to decide out of these two which one. So this is a standard problem in the classification. And you can see the broken leg, it has been given a score on the left hand side image, the 0.91. So it's a 91% probability that this leg is broken and only 0.08% probability of this legs being healthy. And on the right hand side, you can see that the probability for being healthy is 76%, and for broken is 23%. Now, if you compare this both the images, then on the left hand side, you can see the portion of the knee. The portion of the knee is not covered because the knee is a part where you have some sorts of joints, and that joint is a natural joint. It's not a broken part. So on the right hand side, the knee is covered in the image. Now it is quite confusing how the machine will understand that on the right hand side, it's a natural crack. It's a natural like joint, which can be considered as a crack, but it is not actually crack. So it has successfully identified that even if there appears a part of the crack or it seems like a crack when it comes to this knee, but it has successfully identified that's a healthy leg. And on the on the left hand side, it has considered that there are some broken legs. So that's what the application in the healthcare. Another application is the automatic detection of the diabetic eye. Uh, if you eyes are very young, then you might not be problem of person who is suffering from the diabetics, and there is some sorts of blood clots. If you see that the white area of their eyes, there is some sorts of the clots of the blood. You can see their eyes are dots of the. There are few dots of colored red, which are some blood dots. So what that indicates that the person is diabetic, and that dots of the blood is because of the hemorrhage. So if it is a person is a very healthy, then they don't have those red dots in the eyes. But if the person is a diabetic, then they have some hemorrhages in their eye. So this Google has designed this model using the convolutional neural network, a part of the deep learning, and they have trained the convolutional neural network to distinguish. This is a binary classification. You need to identify for a given image whether it's a healthy or the disease. So they have successfully done this in the case of this automatic eye detection. And another, if you can say, you can move one step forward in that detection. The previously it was simply you telling that yes or no, whether the person is having diabetics or not. But again, if I wanted to take this research forward, what I can do is that, okay, once the person has been diagnosed with the diabetics or has a diabetic retinopathy, then where are those lesions available? Can you localize the lesions within the eye image? So there also you can apply this deep learning. So for this classification as well as the localization. So these are the different aspects for the area, but you can see the different aspects of doing the research. So the lesion localization was also done on using the convolutional neural network. So there are several applications nowadays in the healthcare. So let us discuss the deep learning concepts, that how the deep learning is doing all those things, how it is possible for the deep learning to do those high-tech tasks. So for that, we need to first of all understand the nitty-gritty of the deep learning, and for that reason, we need to understand the flow of any intelligent model. So usually, if you have designed the simplest model in the machine learning, let us say the linear regression as well, then you might be aware of this flow. That first of all, we need to get the data, then we usually clean the data. I mean, clean data means that there are some missing data in a particular row. So we either remove or we substitute the data over there. Then after we train a model, if has been already selected, then we go for the testing of the data. And once everything has been done, we can evaluate the model, or we can improve the model if the evaluation reveals that it's a very poor model. So either we change the machine learning algorithm or the deep learning model that we have designed, or we try to gather the more data for these model improvements. So the strategy can be anything is possible depending on your complexity of the problem. So what kind of applications we use in the machine and the deep learning? So we apply this machine learning and the deep learning where there is no deterministic algorithm is available or not even possible with the very high complexity. So in those cases, we apply the either machine learning or the deep learning. And if I want to give a very single example, then let us say the handwriting recognition. So we don't have any deterministic solution for this handwriting recognition. What do I mean with the deterministic? Is that suppose you want to find the simple interest on the amount you deposited in a bank. So that's very deterministic problem that you have the principal amount given, the tenure of this deposit is already decided, the interest rate is already decided. So with this all information, you can successfully calculate the what interest you will earn on the given deposit or the given with the given interest rate. So quite deterministic. You have a very standardized formula. But for the handwriting recognition, we can't have that very specific formula that we apply this formula and it will definitely identify this character is H, this character is B, this character is C. And you can see that we have different languages also. Each person is writing in their own way, having own style of writing. So as a human, we can understand, but for the machine, it is quite difficult to understand. So in this kind of problem where the deterministic algorithm is not possible, you need to either go for the machine learning or you have to go for the deep learning. Then the second type of the problems which don't have a fixed solution and the goalpost keep changing. And in that case, the system has to adapt and learn from the experience. So here, the popular example can be a spam email. So what do I mean with the spam email is that today, let us say I have a model which has successfully identified the spam emails. But now the spammers are also very intelligent. So what do they do? They develop some new mechanisms and ideas so that the models cannot capture those email as a spam. So ultimately, if I have a particular model of the spam, so if today it is working correctly, it is not guaranteed that after 1 month the same spam model will work because the spammers have designed new techniques to overcome this technique, this model. So then after the spam model has to upgrade or have to update to the new things. That means the goalpost is keep changing day by day, and the model has to adapt and learn from the experience. The third thing is that where the solutions are individual specific or time dependent. So recommendation engine, something which is recommended to me is not necessarily can be recommended to the another person. That means a solution is very specific to me, and it is also time dependent. That means 3 years before, I used to like the web series, like the Indian web series. I I watch them, let us say. But nowadays I'm very much busy in my life after after the birth of my daughter. So previously I was searching for the very new web series, which one is very popular, which one is not. But nowadays I'm looking for the diapers, which diaper is very good for the this month old baby. What the medicine they should take so that they can be healthy. So my the requirements for me has changed over the period of the time, as well as it is quite specific to me. So there, in that kind of in this type of problem also you need to apply the machine learning and the deep learning. And finally, you can apply for the prediction based on the past and the existing pattern. So the very example of that the prediction on the share prices. So you need to consider the like the old behavior as well as the current behavior of the particular company, so that you can predict the growth or the future of the share, share price of that particular commodity. So these are the, we can say, the broader aspects. So when you are confused, whether I can go with this statistical model, the traditional models, or this machine learning deep learning model, you can always take this slide as a reference to identify whether it lies, my problem lies in this category. And if it is the case, then you can apply the machine or deep learning. So let's go to the now machine learning. So popularly we are using these are the uh, tools to implement the deep learning concepts. Like we have the Python like environment. We can use the Jupyter notebooks, NumPy for the matrix manipulation and the vector calculation. We can use the Pandas for data handling, curation, and manipulation. We can uh, use this matplotlib for plotting the data for the analysis purpose. So these are just a list of the essential tools which you may need as a deep learning engineer. And the concepts of the deep learning which originates is from the our natural intelligence. So we are trying to mimic the concept. We have not completely copied the concept. The thing is that our natural intelligence is quite relevant and applicable when we study this deep learning. So we have these dendrites and axons where the information is being passed from one data to another using bypass of the axons. So our natural intelligence or the images that we see are stored in a distributed fashion across the dendrites, and that's what the natural intelligence will learn to develop this deep learning. So the first and foremost thing we need to study in the deep learning is that what are the features. So the features are nothing but the elements of your input vector. So if I just will give the one of the example in this so I wanted to predict, let us say, the airline fare particular day in January 2021. What should be the flight fare from Delhi to Mumbai? Let us say I just wanted to go for the prediction. Then I cannot simply predict without having any data. So I need to have the data that how many number of seats I am going to book. Because for one person, the price is something different. For two travelers, the price is different. In which class I am traveling, either economy or the business class. What is my time of journey? If the flight takes 10 hours for a particular journey, like from Mumbai to, let's say, Heathrow Airport in UK, then the time also affects the fare. Similarly, from Delhi to Mumbai is maybe 1.5 hours. So the time is less, the fare can be less. So the time of journey can be another prominent feature. The day of the journey. Usually, on if you're traveling on the weekdays, working days, the price will be something else compared to the weekends on Saturday, Sunday. And the time of the journey also. If your flight is at the midnight, 2 a.m., then the price will be different. And if your flight is at the 9 p.m. in the night, then also the price will be different. It has a time dependent also. Then what is the origin? What is the destination? What is your seat preference? So these are all nothing but the features. The features help us to gather some sorts of the knowledge in the particular domain. So that's what the elements of the features that ultimately help you to design a model. So for different applications, we have the different features. Then after it comes to the concept of the weights. So with each feature, you have the particular weight assigned to that. So I go back to this previous slide, and there are, let us say, for the airline fare prediction, and there are 8 to 9 features. Not all the features are equally weighted. So origin and the destinations, let us say their weight is zero point 0.2 and zero point 0.3. The seat preference is having the weight of the point 0.1. The important thing is that the time of the journey. So its weight is more because it is quite crucial feature to predict the airline fare. The day of the journey is also very crucial features to decide the airline fare. So they are more important, so the more weight associated with those features. So the weight decides what? The weight decides that how much the particular feature is important for the model. If the particular weight is very less, that means it has some impact, but not that significant impact on the model's performance. And usually what we do, we don't know initially the weight for each and every feature. So we randomly assign or we randomly initialize the weights, and then after the models, whatever they will predict, and this prediction and whatever the actual outcome, the difference between them, so the error. So from that error, it changes the weights again in some direction based on this optimization theory, and gradually it will output the importance of the features. So that indicates that this particular feature is important and this one is not important. Then after the another thing that we wanted to learn is that the loss function, or we can say the loss function is what, suppose you have predicted something which is not as per to the actual outcome. So there is some sorts of error. Error is called, we can also call the absolute error. But that absolute error will not be always positive. So we can say that loss will not always be the positive. Sometimes we have the positive value, sometimes we have the negative value. But again, both the things are the difference. So if we don't consider this positive and negativity, then ultimately when we sum up them, it may end up to the zero also. So in order to avoid that situation, what we used to do is that we apply the loss function and the error difference will be always squared, so that we get the actual idea that how far the model is predicting and how far it is not accurately predicting. So the benefit is that we square this error difference because it always gives a positive value, so that the sum will not be zero. And the squaring emphasizes the larger difference. So let us say I have to predict the age of a person. So the age is 5 and I have predicted the 7. So the difference is 2. Suppose the next time the age is 5 and I have predicted 3. So the difference is -2. So when I will add this 2 and -2, then ultimately it becomes 0. But suppose that I have squared each time. So the first instance, if the difference was 2, I have squared, so it becomes 4. The second time the difference was -2, but I have squared, so it becomes again +4. So this time, while squaring, we get the positive value as well as the differences and emphasize more. So this time we can say the difference is 4 instead of 2. So that will ultimately help us to identify whether that feature turns out to be good or bad. And sometimes it also helps us to identify whether the particular is quite important or not important. So we can also consider the feature as an outlier, that the feature is not at all important. So that's what the loss function help us to understand. And then we come to the architecture of this deep neural network. So the deep neural network architecture is uh, quite similar to this neural network, where we usually have this input layer, hidden layer 1, hidden layer 2, and may have several hidden layers then after, and ultimately we have the output layer. So what the the important thing over here is that those circles in the input layer or in any layer are considered as a, like the neurons. It can be considered as a, like say in terms of this natural intelligence, we used to have this actual neurons, but here we can consider as a computational node. So you can see that from the input layer to this hidden layer 1, all the neurons in the input layer are directly connected with the hidden layer 1, and vice versa from the hidden layer 1 also from to the hidden layer 2, all the neurons are connected with the rest of the neurons. So this is called as a fully connected deep neural network. So if I wanted to explain that how these neural networks are working, so let us take an example with a single neuron in the first hidden layer. So what we are trying to achieve over here is that I have taken an example of the airline prediction. So let us say 1, 2, 3, 4, 5. There are 5 features. So with each feature, I have associated one neuron. So that can be like the x1, x2, x3, x4, and xy. So this x1 to xy act as the input layer. And then I have the hidden layer where there is only one neuron available. So as per this neural network concept, all the neurons in the input layer will be connected to all the nodes in the hidden layer. So therefore the x1, x2 up to xy all are connected to z1. That is the neuron in the first hidden layer. And in addition to that, with each hidden layer neuron, there is a bias associated. So the bias is already connected with the Z1. And we already know that each feature has associated weight. So we have the phi features. So we have the phi weight W1 to W5. And what ultimately we are trying to do is that this Z1 is computed as the X1 multiplied by W1 plus x2 multiplied by w2 up to xy multiplied with w5 plus b. So this z1 is having a value of the summation of the multiplication. And then what we try to apply is that this z1 function z on the z1, which ultimately help us to go with the predicted output. Now the predicted output, let us say we designate with the y cap. So the predicted, if it is a y cap, and if I say the yi, or we can say simply y is the actual outcome, then we are always interested the error in the model. So we can take the difference, that is y cap minus y. As per the loss function, we have to square them. So we have squared. So this is the prediction for the first sample. So that is why we have to, if I have the m number of samples, then we have to start with I is equal to 1 to m, that is the y cap I minus yi square, and all the differences when we accumulated divide by the number of samples, we get the mean squared error. So that's the way you can compute this mean squared error of the particular model. So now you can see that here in the previous case we have multiplied this x1 with w1, x2 with w2. So ultimately what we are trying to do, we are multiplying the weight vector with the feature feature value, that is the x vector. So why we are doing this w transpose x? So you can simply see that we have this x vector, we have this weight vector. So this matrix, if you can see, the dimension is 5 cross 1. Again, this weight vector is the 5 cross 1 matrix dimension. And the multiplication of these two matrices is not possible because the dimensions are same. So what we need to do, that we need to change the dimension of the second vector. So if I just make it as a row vector, then the dimension will become 1 cross 5. And now we can easily multiply both the matrix, and the output matrix will be generated as a, so 5 cross 1 cross 5. Okay, so we can now multiply both the matrix to generate the single value. So in this case, you can see that both the vectors, when they have multiply and added, we get the single value z1. We can say the scalar quantity we have achieved. So that's why we have to go for the W transpose X. And you can also see that after getting this value z1, we have applied the activation function. So what is the role of the activation function? Why do we need them? So the activation function is applied on the every neuron, first of all, in the layer. So output from the every neuron is generated after applying the activation function on the value z1. So why it should be applied? Because we need to transform the input value to a different space in the domain so that we can do some sorts of threshold. So if I wanted to give an example, that the output is range from minus 500 to let us say 5000. So the range is quite spreaded. So what I can do, I can transform that range into the 0 and 1. If I transform them into the domain of 0 and 1, so it can be easily applied, like the 0.5 will be the threshold. Anything beyond the 0.5 will be positive. Anything less than 0.5 will be considered as the negative. So those kind of thing we want to do, there we have to apply the activation function. And the most popular activation functions are this value, that is the rectified linear units, the sigmoid function, softmax function, and 10h function. Each function has different application, but these are the various activation functions, and those are the popular ones. And then it comes as the bias. So if you can see, if you go back to slide, I have mentioned that in addition to these features and the weights, each neuron is having the bias B, which is already added while performing the computation. So why we need to add the bias? So that is also the very fundamental concepts to introduce the bias. So let us understand with the help of the image on the right hand side. So on the top image, you can see that each and every curve, whether it's a very steep curve or it has the very less uh, slope, in each case, the particular curve is passing through the center line. That is the output, the point 0.5 in the y-axis and 0 on the x-axis. So if it is a very steep curve, then also it passes from point 0.5. And if it is a very less slopey curve, so that also passes from the point 0.5. But that's not always our input data will be. Our input data is not necessary to be passed through the center line of the 0. So what can be done if the data are not passing through the 0, then we have to move the curve left and right. We have to change the direction of the curve to the left and right. And by introducing the bias, what we can do, we can better fit our curve to the given input data. So bias only influences the output values and it doesn't interact with the actual input data. And that's what the purpose of introducing the bias. And now we come to this computation problem of this deep learning. So let me have a break for a water. Okay. Mm, So we can quickly understand that how to start with the deep learning. So let us say we have the image and we all know that it's in the format of RGB, so red, green, and blue. And let us take an example that the image size is 8 cross 8 and there are three dimensions. So the third dimension we have the red, green, and blue. So it will become 8 cross 3. So ultimately it will be like 192 pixels. So first of all, for any image, we have to that into the form of the vector, because if you can see, when we move towards this neural network, the input layer is nothing but in the form of the vector. It is not in the form of the two-dimension image. So anything we have like a two-dimension image, we have to first of all convert them into the vector so that it will become our input layer. So therefore, this image, which is having a three dimension, we have converted them into the input vector, which is having the size of 192 values in the input vector. Now, what we can do, that is for the single image. So for a single image, we have one vector of this 192 values. Now let us say we have m number of images are available. So if I want to visualize the concept, so let us say a single image is having the n values in a vector. So that will be the first column. That means the image value. So the image 1, the value 1, image 1, value 2, image 1, value 3. So that is the first vector where the first image is having the n values. Then we have m such images. So it will become the n cross m shape. So the number of IO pairs available for the training networks will become n cross m. So you can see that the last mth image is again having the n value. So that's why the x m1, x m2, x m3 will be the input vector. And for each image, let us say I'm going for the binary classification. So there will be associated value y, which will belong to either the class 1 or class 2. So what will be the shape of the output class if it is a binary classification? So it will be again a vector. So this y1 indicates for the first image the output value. This y2 indicates that the output for the second image. So similarly, we have the m number of images. So we have m outcomes, or we can say each outcome belongs to either of the category. So the shape will be 1 cross m. And now let us understand the inside story of this neural network. So let us say we have these three neurons in the input layer. Then in each layer of the hidden layer, we go for the computation. So what we are computing? W transpose X. So here we have this X1, X3. Let us represent them with the X as a feature vector. And this, if the neuron is, let us say the first neuron, what we can say, the W1, 1. So that indicates the weights for the first neuron in the first hidden layer. Then the weight for the second neuron in the first hidden layer. The weight for the third neuron in the first hidden layer. So this way we can go for the computation W transpose X plus B1 in order to find the Z1 in the first neuron. So in the first layer. And then after we apply this sigma as an activation function, so that it will give us the A1, 1. If we have the second layer, and if there is only one neuron, then again the computation will repeat. So here what we have, since the second layer, so we have inside the bracket we have written 2. So this the bracket represents that the layer. So here on the top the notation is given. If it is A, L, I, so that L indicates the layer and A and that I indicates the node in the layer. So since in the second layer we have only one neuron, so the subscript is always 1, but the superscript is 2 because it's a second layer. So again, there we go for the calculation of the neuron value Z1 bracket 2, and then we apply this activation function to go for the final prediction. So this is the way we can understand how the neural network can be represented. And then we have the different activation functions. So I explain the softmax function because it is very popular for the classification of the multiple categories. So if you have only binary classification, then it's a different issue. But when we have the multi-class classification, then we can go for this softmax function. So suppose you have this ImageNet data set. So there are very different types of images are there, and there are 1,000 classes are there. So there you have to apply the softmax function. So because the problem becomes the multi-class classification problem. So that is what the usefulness of the softmax function. And now let us go into the convolutional neural network. So these are the different application of the convolutional neural network. We have already seen that for the face recognition, style transfer, image quality enhancement, classification, gesture recognition, etc. So I'm not repeat them, but the motivation is quite important for this convolutional neural network compared to the fully connected neural network. So let us say we have one input image of the 16 cross 16 size. So as I already mentioned that the two-dimension image cannot be given as input to this neural network. We need to transform them into the vector. So the 16 cross 16, so ultimately 256 neurons. So that will be our first layer in the input. And then let us say we have only one hidden layer, and then after we have the output layer of the character recognition. The output layer will be having the 26 neuron because we have 26 alphabets in a uh, we have because we have 26 alphabets. So for this particular processing unit, what will be the complexity that we will first of all understand. So here we have this 256 neurons in the first layer, and each neuron is having the associated weight because this neuron in the input layer indicates the features. Now those weights are multiplied with the neurons in the first hidden layer. So for example, let us say there are 100 hidden units. So all those hidden layers, like each and every neuron in the input layer will have the connection with the each neuron in the second layer. That means the 256 neurons will ultimately have the multiplication with the 100 neurons in the first layer. So that is 256 multiplied by 100, and each hidden layer will be having the bias. So there will be plus 100 biases will be there. Now from the second layer to the third layer also there is fully connected layer. That means each neuron will again have the multiplication with each neuron in the output layer. So 100 multiplied by 26 output neurons plus 26 biases of the output layer. So when you will together multiply everything, you will be having a 28,236 trainable parameters. So this is a very small neural network with only one hidden layer. Now you have the multiple hidden layers, then you can assume the complexity of the trainable parameters in this particular case. So it is not useful if we have to train that many number of parameters for such a small network. And we need to identify some new concepts so that we can minimize the number of trainable parameters, but at the same time, we can achieve the accuracy. So you can see that in the fully connected artificial neural network, there are the lots of the edges over here. So is it possible that if I remove some of the edges, then also I can have the better predict, I mean, have the maintain the prediction accuracy. So from the fully connected model, do we really need all these edges? That is what the first of all concept. If not, because you can see the computations are repeated most of the times. The same computations are carried out by the different neurons several times. So if we can remove those redundant computations, then we can achieve the same performance, or we can raise the same performance. That's what the possible. And can some of these ages be shared among the neurons? So this is another question that arises out of it. And what we can understand out of these two questions, that even if we remove some of the ages, is it possible to maintain the prediction? So that concept can be understand from this particular video. So I'm going to run this video where we are gradually removing the information, but at the same time it helps us to understand that this is a image of the dog. So let us first of all see the video, and then after I will let you know that what is the importance of the video. So our fundamental question was that all the ages are needed. We can say no, because you can see this particular image of a dog in the first iteration. We have removed the 50% of the ages. Like we are selecting and we are removing, selecting and removing. But even if then we have removed the 50% of the image, we can still recognize that this image is of the dog. We have not stopped there. We have taken that image and again we have go for the second iteration. So ultimately we are now left with the 25% information only out of the 100. We have removed 75% of the information. So this each piece of the image represent the 25% of images of the original image. But you can see that uh, each of that image still recognized as a dog. That means it is not always necessary to retain, or we have need 100% of the image for the object recognition. But if we remove some redundant information, then also the object recognition is possible. So that what the answer of the uh, those two questions, that fully connected, not the necessity. But if you have them, then you will be having a lot of computations. So now we just come to the approach of the CNN versus ANN. So we concluded that the ANN suffers from the curse of dimensionality. And what we need to do is that we use the filters to exploit the spatial locality by enforcing the connectivity pattern between the neurons of adjacent layers. So curse of dimensionality means that there are lots of unnecessary informations are there, which unnecessarily increases the computational requirement. And the thing is that now what we need to do is that suppose we have removed the information, but now we need to connect the patterns by using the spatial locality. We have to spatial locality. What do I mean by that? All the adjacent pixels represent the same things. That is what the concept. So if you have the let us say taken a picture of this my face, then most of the time you can see the skin colors are same in the nearby pixels are having the same intensity, except there are some edges which appears. then there will be a slight difference, and then again the adjacent pixels will be having the same value or most of the similar intensity. So that's what we call as exploiting the spatial locality. So, and therefore the concept of the parameter sharing and the sparsity of the connection has arisen. And for that, what we need to do here, you can see we have mentioned that we use the filters. So those filters are nothing but we can assume them as a type of the matrix which are used computation. So we quickly go with this convolutional process. So the process of convolution is a pointwise multiplication of the two functions. And ultimately, after applying this convolutional features, convolution process, we end up with a convolved feature, or we can say the feature map. So I explain this convolution process first so that we can understand. So this is in the center one, we have used a 3 cross 3 filter. So this is the filter which will exploit the spatial locality. So let us see that how we are exploiting the spatial locality. So on the left hand side, there is an input matrix of the 6 cross 6 uh, size, let us say generalized is n by n and having some value. We have this filter 3 cross 3 generalized f cross f. So is what the pointwise multiplication. So I will run this filter on the input image in a pointwise multiplication so that I will get the output matrix. So in the first case, if you apply this filter, so you can have this let's say 3 cross 1, 0 cross 0, and 1 cross 1. So when you will multiply each and every cell, you will be having the output value is the -4. Then you will move the filter one step on the right hand side. Then again you will go for the pointwise multiplication. You will get the another value that is -4, then 0, then 8, and then you will run this entire feature on the entire image. So the output will be always considered as a convolved feature. So what we have done, we have removed the significant amount of information, but at the same time we have the pattern in the form of the convolved feature. And the size of the convolved feature can be calculated with the formula of n minus f plus 1. So input is 6, f is having a size 3, so 6 minus 3 plus 1, so it will be a 4. So if we have the n cross n input image, filter size is f cross f, then the convolved feature map will be n minus f plus 1 cross n minus f plus 1. So you can see we are just moving for the pointwise multiplication. So this is the imaginary representation that how this convolved feature can be derived. So you just repeat the process. We are just moving pointwise calculation. So in the convolutional neural network, this is the convolution process. Now, okay, now we come to the part of the detection of the edges. Yes. So in the when we want to detect the edges, there can be vertical edges or there can be some horizontal edges also. So depending on the type of the edge we need to detect, we need to use the appropriate filter. So here in the like the center matrix, like a 3 cross 3, you can see the filter is like a 1 1 1 0 0 0 and -1 -1 and -1. So when you use this type of filter, it helps us to detect the vertical edges. So just want to confirm the case, the input matrix you can see it's a 6 cross 6 where the first three columns are 10, then the later three columns are 0. So there is a vertical column over here in the image. This 10 and 0 are nothing but the intensity of the pixel. So where have they like the very sharp change in the intensity of the pixel, which is represented as the vertical image. Now you apply this filter on this image and you get the convol matrix as a 0, 30, 30, 0, 0, 30, 30, 0. So you can see that 30 and 30 is what? It is identified as a vertical edge. So that's what the beauty of this filter process, or we can say the convolution process. So we have the different filters available depending on our requirement. So if you wanted to detect the horizontal edge, then you this horizontal filter. There is a 1, 1, 1, 0, 0, 0, and minus 1, minus 1, minus 1. So when you run this filter on the image, from the entire image, it will identify all the horizontal images. Then for any type of image, whether it's a horizontal, vertical, or anything, if you wanted to detect the edges in the image, then you can apply this Sobel filter. So this Sobel filter is a very popular filter. Those who have studied this image processing, very popular invention in the case of this image processing. So that is 1, 0, minus 1, 2, 0, minus 2, 1, 0, minus 1. So there's a Sobel filter can detect any edges in the image. So there are different filters according to the use. We need to choose as per our convolutional requirement. And if you want to just get the more intuition over here, how the edge detection can be performed. So we have taken an image over there on the left hand side, the mouse, and we have run this filter of size 7 cross 7 filter. And when we run this filter over there, you can see that the pixel representation of the filter, it has successfully identified the uh, edge of the mouse. So that's what the way you can understand how the filtering process or convolution process is being carried out. And after this process, just wanted to give one intuition here that when we applied this convolution process, what happened that our input dimension is n cross n, but the output dimension is not the same after the convolution process. So suppose I give you an example, we give an input image to the machine for the object detection, and it has output an image which is less in the size. So that's not always desirable that you provide the input of something and the output is having a different size. We wanted to have the object detection, but at the same time, we want to maintain the image size also, output size. So there, what we need to do, we have to go for the padding. So padding, what it does, it used to preserve the original dimension of the image, or we can say the input, and the zeros are added outside the zeros are added to the outside of the input. And when we apply this padding process and then after we go for the filtering, we can maintain the size of the input original dimension. So you can see the formula for the padding is n, if it's the input size is n cross n, the filter is the f is a, let's say f cross f or 3 cross 3. Then by adding the padding is equal to 1, we can have the same dimension of the images. After the padding, we have the concept of the strides. So that means no need to move the one column at a time for the filter, but we can jump the filters for few columns and the rows also. So you can see that 6 cross 6 is the matrix input size, 3 cross 3 is a filter, and striding is equal to 3. That means when I will move this filter on the original image, first of all, I will compute the convolution. Then after I will jump 3 columns. For the row also, I will jump for the 3 rows and then after go for the computation. So you can see the 6 cross 6 is the input matrix size, but the output size is just 2 cross 2. Because of the striding is equal to 3. And there is a standard formula for the calculation of that output image size. And there is a pooling layer also. We have the max pooling layer, mean pooling layer. So max pooling is what? Out of this uh, filter area, we take only the maximum value. So that's what the max pooling. So you can say on the left hand side, we have the values 1, 4, 1, and 8. So we have taken the maximum value 8. Similarly, we have taken the second maximum value is a 9. So this is what the pooling layer. There is another way that we have the average pooling, where the average is calculated. And finally, if you have successfully understood the convolution process, padding, max pooling, so there's the pooling layer, we can easily understand that how the deep learning model like this AlexNet convolutional neural network has been designed. So it's a standard deep learning approach has been applied in this AlexNet, where there are several max pooling layers in the convolution process are applied, followed by this fully connected neural network. And finally, this AlexNet model is designed for the ImageNet dataset where there are 1,000 classes. So therefore, at the end, the softmax function is applied for the multi-class classification to predict the classes among those existing 1,000 classes. So if you want to understand how this all the calculations and the numbers appears in this AlexNet dataset, let me just give you a brief example. Is same the understanding the AlexNet in detail. So the input dimension is 227 cross 227, and there are three channels like the red, green, and blue. And first of all, they have applied the convolutional process with the filter size of 11 cross 11, and stride is equal to 4. And there are 96 kernels are used. 96 such kernels are used. So if you can follow this convolutional equation, so what they have to do n. So n is 227 minus f. The f is what the filter matrix size, which is 11 cross 11. So 227 minus 11 divided by the stride. So here the stride is 4. So that means 227 minus 11 by 4 plus 1. That will be the standard formula. When you will apply that, you will get the output as a 555. After the first convolution process, your image, which was of the size 227 cross 227, has been changed to 55 cross 55. And since we have used the 96 such kernels, our third dimension size will be 96. So if you're unable to recall the formula of the convolution, let me just go back. Here you can see the formula is n minus f plus 1. So that's the process for the convolution. But if you have this stride, then you have to divide by s also. So therefore, over here, we have the output is 55. Now you have applied the max pooling. So max pooling has a standard formula is n minus filter size divided by stride plus 1. So that's why 55 minus 3 divided by 2 plus 1 will be 27 by 27. So this way we have applied several convolutional process and the max pooling, we can say the pooling process, to finally change the image size to 6 cross 6 with 256 filters. So from 227 cross 227, they have changed the size to 6 cross 6, which ultimately have the vector size of 9216. And then after they have applied this fully connected neural network to finally go for this final prediction using the softmax. So this is what the entire concept of the deep learning. Depending on your application, you have to decide the convolution number of convolutional process and number of the pooling process. So this is just an AlexNet architecture designed for the ImageNet dataset. But if you use this same architecture of CNN architecture for your application, it may not predict accurately. So therefore, you need to change the convolution and the pooling process. So that's what the entire journey of the deep learning. And there are some famous CNN models we have seen, and many of you might be using them also, like the VGGNet, then ResNet, Inception, AlexNet, GoogleNet, etc. So you can explore these models in detail to understand how they have designed the convolution process and the pooling layers, etc. So that's what the journey of this healthcare using the deep learning. So our job is to understand how the deep learning process or the concepts are working. I think I should conclude over here. So I will be concluding. Thank you very much for joining, guys. So if anybody has some questions, then they can feel free to ask.
Thank you, Dr. Hiran. Thank you very much. Hello, dear participants. Do you have any doubt, any query? Please ask Dr. Hiran. Dr. Hiran is with us, so he will spare a few times. So if you have any doubt, you can ask. And this is perhaps the last session for Dr. Hiran. So if you want to interact with him, you can ask any questions, dear participants. I think they don't have any. I will check the chat box if anybody is there.
Okay.
Yeah.
Okay. If anyone wanted to connect with me, what they can do, they can go to my website also for more detail, and they can write an email to me also. So if any one of them are interested to collaborate on any research areas, then I will be happy to join them.
So, my dear participants, I request to all of you, please keep in touch with all academicians. We all are academicians. So sometimes you may need any kind of research collaboration or any kind of research facilities be it available in our organizations or in your organizations. It is a win-win solution. If you will work with us, we also will take interest, will work with you all. So yes, anybody is having doubt? Anything you want to ask? So Dr. Hiran is also a very good publication, and he is doing very good research also. So if you want, if you are interested, then you can collaborate with him. And we also started the collaboration with him, and we are also doing some works. And in future also we will do much more thing. So we invite here if anybody is interested to be the joint venture with Dr. Hiran and with us, then you are welcome. So thank you very much, all participants. Thank you, Dr. Hiran, for your kind support, and you spend your valuable moment, and you said a lot of important things related to machine learning, image processing, and mainly for the medical images. So, and I hope definitely few of our participants may connect with you, and they may want to proceed together, and definitely we will work. uh, so thank you very much for your informative sessions, and what other formalities we have, I will communicate to you over mail, so that the next step we will process.
Okay.
And okay, sir. Okay, thank you very much. Anybody, please? Any questions? Otherwise, we'll wind up the session. I have already shared the attendance and feedback link in the chat box. So please look at the chat box, please. Those who have joined late, they may not have seen the chat box. So thank you very much. Thank you very much, Dr. Hiran. We will meet again. We will discuss.
Okay, thank you, Dr. Uday Kumar Tripathi. Thanks for participants joining the session. Forward to have some nice collaborations. If you guys are interested to collaborate, then please reach to me on my official email ID, and I have also shown my websites there. You can also reach to me. Okay, thank you guys for joining.
Thank you all.